Hello everyone, welcome to another lecture of chemical bonding class 11. Myself Suman Singh. So in the last class we have discussed about the Lewis dot structure and Fajan's rules and all, right, and octet rule. So today we will see the limitations of octet rule and valence bond theory. Okay, so when we talk about the limitations of octet rule, first limitation is it fails to explain the stability of incomplete octet. First is what? It failed to explain the stability of incomplete octet. For example, BH3, BF3, BCl3 or AlCl3. It failed to explain the stability of incomplete octet, as you can see here in case of this. Okay, now second one is it failed to explain the stability of expanded octet. Okay, expanded octet, it failed to explain the stability of expanded octet. Okay, it is possible in those molecules having vacant d orbital. We know that the element which has a vacant d orbital, they used to show expanded octet, right? So this octet rule failed to explain the concept of, or we can say that it failed to explain the stability of expanded octet. Okay, now third one is it failed to explain the stability of odd electron spaces. The element, or we can say that the atoms which has an odd electron, it failed to explain the stability of odd electron spaces in case of, you can say, NO2 or ClO2. It failed to explain the stability of odd electron spaces. Okay, now next one is it failed to explain the stability of the duplet structure of hydrogen atom. Okay, we know that hydrogen show a duplet, right? So it failed to explain the stability of duplet structure of hydrogen atom. Okay, now next one is it failed to explain the stability of cation transition metals. Okay, cations of transition metals which contains 18 electrons in its outermost shell. In case of, you can see some of the example is given. This one Ga3 plus, Cu plus, Ag plus, Zn2 plus, Cd2 plus. So it failed to explain, as you can see, the when you will see there is an 18 electrons in the outermost shell of its outermost shell, or we can say outermost orbit. Okay, so it failed to explain the of uh, stability of transition metals which contain 18 electron in its outermost shell, right? Now next is it also explained, it has failed to explain the chemical means what, inertness of, no, means, you can say like this, it failed to explain on the chemical inertness of noble gases. Okay, but some noble gases able to form a compound like XCF2, KrF2, right? Because according to the octet rule, these inert gases, or we can say noble gases, are stable, right? And they do not form bond, because since they have a complete octet. But we have seen that some of the noble gases used to form compound like XeF2 or KrF2, like this, etc., right? So octet rule based on the chemical inertness of the noble gas, but some noble gases able to form a compound like this one, right? So it failed to explain this concept also. Now next one, when it does not talk anything about the geometry of the molecules, right? You have seen that in all the cases whatever we have learned in octet rule, they have not discussed anything about the geometry of the molecules, right? Now next is it failed to explain the relative stability of the molecules. Okay, so I hope you have understood about the what are the limitations of the octet rule, right? Now next we will see the valence bond theory. Okay, now when we talk about the valence bond theory, right? So before starting the valence bond theory, I will give you one example with that will help you in understanding the valence bond theory. Okay, let me draw one structure. Suppose you see here, this is the structure. Okay, so when you will see this structure, this is a nucleus, right? This one is nucleus and this one is nucleus. Suppose when these two, what according to valence bond theory, when the two electrons approaches each other, there is exist a four type of, means what, there will be there will exit exist either repulsion or attraction. Okay, so we will see when this two atoms approaches each other. First of all, suppose this is an electron here, right? Suppose this one is electron and this one is electron. So first of all, what will happen, if they two will come closer to each other, there will be a repulsion, right? As you can see, there will be a repulsion between these two electron, right? Next, what will be what will happen, there will be a attraction between this nucleus and this electron, right? Second thing. Now next is, again, there will be an attraction between this electron and this nucleus, right? And there will be a repulsion between this nucleus and between this nucleus, right? So there are four criteria we are getting from here. First is force of electron, okay, and force of electron. Between them there will be a force of repulsion, okay, I am writing R for repulsion, right? And after that there will be a force of neutron and neutron and neutron, or a nucleus and nucleus. So there also there will be exist a force of repulsion, right? Force of repulsion. After that, again, if you talk about the force of attraction, so force of attraction will be between electron of one this and the nucleus of this, right? And the nucleus of this. Another one, force of attraction will be between the electron of this and the nucleus of this. So see, these four type of forces exist between when the two atoms come close to each other, okay? So always this one, I hope you have understood, right? When the two atom approaches each other, you can see that there will be a repulsion between this and this, right? And at the same time there will be a attraction between this and this nucleus, right? And after that there will be an attraction between between this electron and this nucleus, okay? And after that there will be a repulsion between this nucleus and this nucleus, right? So these are the four uh, we can say forces exist when the atoms come close to each other, okay? So I am erasing this one. So always remember that if the net force of attraction, when this bonding will be possible, bonding will be possible according to the valence bond theory. Bonding is possible only when the net force of attraction is greater than the net force of repulsion, okay? Or if the net force of attraction is equal to or less than force of repulsion, net force of repulsion, at that time bonding is not possible, okay? So I am erasing this one. I will write here. So always remember that when the force of attraction, okay, or we can say net force of attraction is greater than net force of repulsion, okay, net force of repulsion, at that time only there will bonding is possible, okay? If net force of repulsion is greater than net force of attraction, then bonding is not possible, okay? So I hope you have understood this concept, right? Now next thing what he says, that he said according to valence bond theory, atoms must come closer for overlapping, okay? When there will be when will the bond will formed, when the atoms will come closer, okay? Or when they will come closer, there will be an overlap. After that only the bond will form. Suppose we are taking the example of this graph. Suppose this is energy here, and this is suppose internuclear distance, okay? Suppose this is internuclear distance, okay? Internuclear distance. So what will happen, suppose here is one atom, here is one atom. So you can see that when they are very far away from each other, what will happen, there will be, when they will be very far away from each other, at that time what will happen, when they will come closer, there will be a decrease in energy, okay? Like this, there will be a decrease in energy. So this distance is called what, this is the point where the bond is forming, okay? And this is also called what, bond length. Here the bond length, when you will see, it will be approximately 74 picometer, okay? So at that time the bond will formed here, okay? This is the bond, right? So for the formation of bond, there should be an overlapping of orbital should be there, okay? If the atoms must come close and overlap to form a bond, right? Second thing. Now next is he told that there should an orbital configuration. So he told that there should be an orbital configuration. Means what he says, that suppose this is a one of orbital and this one is another orbital. So he says that either this orbital should have one electron and this orbital should be empty, okay? Then only the what will happen, suppose this one this orbital is one electron, and this orbital is also having one electron but in the opposite spin. So at that time they will bind together. Okay, at that time what will happen, they will bind together like this. At that time, let me draw it like this. At that time they will bind together like this and they will form a bond here, and the electron density will be here. Okay, or second thing what he said, that either this orbital, when we talk about this orbital, either this orbital should have two electrons and this orbital should be empty. At that time also they will form a bond. Okay, at that time also they will form a bond, and the density will be, electron density will be here. Okay, so this was the second concept about the orbital orbital configuration. Now next in what he says, that extent of overlapping, okay, will depend on the strength of bond. Suppose this one is this one is one overlapping, suppose, and this one is suppose another overlapping. Okay, and one is like this, one is suppose like this. So you see here the overlapping is more, right, as compared to this. So here the bond will be stronger. Okay, as compared to this. Again, if like this is there, the overlapping is like this, right? If one bond we are taking, if overlapping is more than this, here more overlapping is more, right? So this one will be stronger bond than this. Okay, so always remember that what is this valence bond theory. Actually this valence bond theory was given by Hitler in London. Okay, and after that it was extended by Pauling and Slater. Okay, so whatever I am talking about is this concept was given by Hitler and London. Okay, so now what did he says, the last point, the extent of overlapping will be directly proportional to strength of bond. Okay, if more overlapping is there, the bond will be strong. If less overlapping is there, then bond will be weak. So this was about the Hitler and London concept of valence bond theory, right? Now next we will see extended means what, Pauling and Slater. After that what he had what they did was they expanded the concept of this valence bond theory. Means they have expanded, means whatever the some of the things which was not explained by this Hitler and London was explained later on by Pauling and Slater. Okay, so first thing what Pauling and Slater told about this was extent of overlapping depend upon two factors. Okay, one is nature of overlapping orbitals. Okay, and another one will be nature of overlapping. Okay, the first thing that Slater and London told about the valence bond theory is that he told that extent of overlapping will depend upon the nature of the orbital, overlapping orbital, and the second is nature of overlapping. Okay, first thing. Now next, second thing what he said, what they have told about this was, more closer the valence shell are to the nucleus, more will be the overlapping. Means what he said, that one overlapping will be stronger than 1 2 overlapping, which will be stronger than 2 2 overlapping, which will be stronger than 2 3 overlapping, and which will be stronger than 3 4 overlapping, and etc. Right? So more closer the valence shell are to the nucleus, more will be the overlapping. This was the second concept given by Slater and um, Pauling and Slater. Okay, now next, third thing what he says, that directional orbitals show more overlapping. Means what, if SS overlapping is there, means what he says, that SS overlapping will be more. Let me write here. As you can see here, it is written, the strength of the bonding depend upon the extent of overlapping. This one we have told, right? And overlapping of orbital is higher and the bond form is stronger. As you can see, overlapping of SS orbital, SS overlapping is more stronger than SP than PP, right? So what we can say, the direction of the bond formed is the direction in which the bonding orbital is oriented, right? So this was some of the concept given by valence bond theory, and what we can say that extended by that and this Pauling and Slater. So I hope you have understood about the valence bond theory, right? So valence bond theory is actually a concept based on overlapping. Okay, so when we talk about the overlapping, so overlapping is generally three type. Okay, one is positive overlapping. Okay, another one is negative overlapping, and the third one is zero overlapping. Okay, So first of all, always remember that between px and py, okay, between py and pz, or between pz and px, here always remember that overlapping is not possible, okay, overlapping is not possible. Always remember that px will never overlap with py will not never overlap with pz, and pz will never overlap with px, okay. Now we will see overlapping and type of overlapping. So overlapping is generally overlapping of atomic orbital is generally three types. One is positive overlapping, another one is negative, and the third one is zero overlapping. So we will see what is positive overlapping. So if suppose we have like this, okay, this one is either, this one is also plus, and this one is also plus, this one is minus, and this one is minus, okay. So this is called what? Sigma pp overlapping, okay, sigma pp overlapping. So this is what? This is a positive overlapping. As you can see, positive side and positive side are overlapping, right? So here what is this positive and negative? Here positive and negative is not a charge, okay, it is just a crust and a trough. If it is like this, we know that the electrons move like a wave, right? Here like this they used to move, right? So suppose they have, we are taking this one as trough, crust has a plus and trough as a minus. So this was just about the crust and the trough, okay, it is not like the charge is not talking about the charge, okay. So when positive charge and positive size of the lab will overlap, at that time they will, this type of overlapping is called positive overlapping. Or one more example you can take. Suppose this is another example, this is a pz, and then this is overlapping with the s orbital, okay. This is called what? Sigma s and p orbital, s and p overlapping, right? So this is also, you can see the plus side, and the plus side is overlapping with one another. This is called what? Positive overlapping, okay. Now one more example you can take, one more example I will give. Suppose we have this like this, and here one is like this and another one is like this, okay. So here also you can see the positive side and positive sides are overlapping, negative sides are no, negative side and negative sides are overlapping. So this is also called what? This is called pi px overlapping, okay. So this is also, you can see positive side and positive sides are overlapping, right? So this is called what? Positive overlapping. So always remember that positive and negative, it is not charge here, it is just talking about the crust and trough, right? Now next is negative overlapping. When one of the positive side, one of the positive side will overlap with another one negative side, then that type of overlapping is called negative overlapping. Suppose this is negative, this is positive, and this is negative. So at that time this type of overlapping is called negative overlapping, okay. One more example you can take. Suppose this is the p and it is overlapping with the s here, okay. So this is a positive side of s, positive side of it, this is a negative side of p, and here positive. So this type of overlapping, suppose this is a pz and this is s, okay. So this type of overlapping is there, you can see positive side, and here it is overlapping with the negative side, right? So this type of overlapping is called what? Negative overlapping, okay. One more example you can take. Suppose this one is here like this one is here like this, here positive. Suppose this one is negative, this one is positive, this one is negative, and this one is positive. So here you can see positive and negative are overlapping, right? Positive and negative are overlapping, positive and negative are overlapping. So this type of overlapping is called negative overlapping, okay. Now next is zero overlapping. Zero overlapping, always remember that if there is a zero overlapping, then zero overlapping is not possible. As you can see, one example I will give. So suppose this is our z-axis, let me write it clearly. Suppose this is our z-axis, okay, and we have like this. Suppose this is positive and this is negative, this is a pz, okay. So if s orbital is coming here, so this is called what? Negative zero overlapping, because this point is what? This point is called nodal plane, right, where the probability of finding an electron is zero, almost zero, right? So since if in overlapping, which one is, who is taking part in overlapping? Electrons are taking part in overlapping, right? But here as you can see, in this portion, here in this portion, the probability of finding an electron is zero. So how this overlapping will take place? Since this is, suppose we have assumed that this S has an electron, but here no electron is there, right? Since this is a nodal plane of this of pz, right? So there, this type of overlapping is not possible. This is also called what? Zero overlapping. Okay, next, one more example you can take. Suppose this is our px, okay, px, and suppose this is our py, this is our py, okay, along the z axis. So here also overlapping is not possible, okay, since I have previously I have told you, right, px and py is not possible, overlapping is not possible, or py and pz overlapping is not possible, and pz and px overlapping are not possible. Okay, so this type of overlapping is called what? Zero overlapping. Okay, so I hope you have understood this, what is overlapping. Now next is type of axial overlapping, or we can say type of overlapping. So there are some first type is ss overlapping, or we can say formation of sigma bond. Next is pp overlapping, which is the formation of pi bond. Okay, so we will discuss what is sigma bond and pi bond. Suppose we have here s orbital, okay, plus s orbital, okay, or number a, sorry, number a, suppose this is s orbital and s orbital, and here suppose s orbital and p orbital. Okay, so what will happen? Suppose we have hydrogen here, here also hydrogen, they both of them will combine to form like this, right, like this. Here also hydrogen, here also hydrogen. So this type of bond is called what? Sigma bond, or we can write also like this: one electron is here plus one electron is here, after that hydrogen, one electron here, like this, right? So this type of bond is called what? Sigma bond. Okay, or one more example for sigma bond. Suppose this is a s orbital and it is combining with p orbital here, like this. So what it will form? It will form, I'm writing here, it will form like this, right? It will form like this. Suppose here hydrogen, here it is fluorine. Suppose we are taking this as a fluorine, let me write it again. Suppose this is our hydrogen, okay, this is our hydrogen, and this is s orbital. Okay, now again what we are doing, we are taking a p orbital. So when we are taking p orbital, suppose we are taking fluorine, okay, so when they will combine, they will form like this. Fluorine will be here, one electron here, and this one. So this is called what? This is, they are forming what here? Suppose there is one electron here, one electron here, plus fluorine. So what they will form? They will form hydrogen, okay, and fluorine is here. So this type of bond is called what? Here also what we can say, sigma bond. They are forming what? Sigma bond here. Okay, there, this is sigma bond, this is sigma bond, they are forming sigma bond. Okay, so I hope you have understood what is sigma bond. Now next is pi bond. So when we talk about, or one more thing, one more example I will give you. If there is a p orbital like this of fluorine, and here also another plus p orbital of fluorine, and here also p orbital of fluorine. Suppose this is positive, this is negative, this is positive, and this is negative. Again they will combine to form what? They will form, they will form what? Sigma bond here, right, like this. Fluorine is here, there is fluorine. Okay, so either so what we have seen, that sigma bond is either with the overlapping of ss orbital, or sigma bond is formed by the overlapping of sp orbital, or sigma bond is formed with the overlapping of pp orbital, right? So we have seen the three example, right? So I hope you have understood what is sigma bond. Now next is pi bond, or so pi bond, always remember that pi bond is formed after the formation of sigma bond. Okay, generally pi bond does not exist independently, but in some cases it is possible, we will see that. So but always remember that for, in according to the valence bond theory, the pi bond will form, sigma bond will form first, and after that pi bond will form. Okay, so for how this pi bond are formed, we say that suppose this is our nodal plane. Okay, so here is one pi, one electron, like this. Okay, so what will happen at that time when they will combine? This is what? This is Suppose this is divided like this, okay. So at that time what will happen, they will, when they will combine, they will form like this, right? They will form like this. Suppose this is a nodal plane here, is a nodal plane. So electron density will be above the plane and one will be below the plane, okay, like this, okay. So always remember that if this is what they are overlapping here, they will overlap like this, they will overlap like this, and they will form pi bond like this, okay. So nodal plane will be this. So always remember that if pi bond is formed between py and py, okay, if this py and py is forming a pi bond here, so at that time the nodal plane will be, always remember that the nodal plane will be zx, okay. Now again, if the pi bond is formed between px and px, okay, so at that time always remember that the nodal plane will be what, yz, okay. And if the pi bond is formed between pz and pz, at that time nodal plane, always remember that the nodal plane will be x and y, okay. So I hope you have got this. So one example I will give you. Suppose this is our suppose this is our carbon here, and here is carbon, okay. Suppose this is hydrogen here, this is hydrogen here, one hydrogen is here, another hydrogen is here. So what will happen, there will be a formation of pi bond, one sigma bond will form first. And suppose this is the orbital here, this is the orbital of this orbital is this, like that. So they will form what, there will be a overlapping here like this, they will overlap with each other and they will form pi bond, okay. So I hope you have understood what is pi bond, right? Now next is we will see the difference between, what is the difference between sigma bond and pi bond, okay. So first is, as you can see, first one is, it is a stronger bond, okay. Next one, it is a weaker bond. Pi bond is a weak bond, okay. And it is formed, it can be exist independently, but it exists along with the bond, pi bond, a sigma bond, okay. Now next is, it allow the free rotation of the bonding atom, and it restrict the free rotation of the bonding atom. I will give you one example. Suppose this is one ball and this one ball, so we can easily rotate this, right? We can easily rotate this, but when there will be a pi bond, at that time we cannot rotate this, right? There will be a restriction because of this, right? So sigma bond, in sigma bond there is a free rotation is possible, but in pi bond free rotation is not possible, right? Now next is, the electron cloud of the sigma bond is along the thinner nuclear axis of the bonded atom, but here the electron cloud of the bond lies above or below the axis, as we have told you, right? It will lies above or below the axis, there will be a nodal plane, right? Now next is, all orbits just like s, p, d can form sigma bond, but except s orbit, all other orbit can form pi bond, okay. Now next is, s orbit will not form pi bond, okay. Now next is, bond both pure and hybrid orbital can form sigma bond, but hybrid orbital cannot form pi bond, okay. Next is, the bond is formed by the axial overlapping of the orbital, as you have seen, I have already told you, right? But here the bond is formed by the lateral overlapping of the orbital. What I have told you, axial, this is what, this is axial overlapping, right? And this is what, this is lateral overlapping. Here there is a lateral overlapping, right? One more example, you can say, we can also define like this, that the sigma bond is formed by end to end overlapping of half filled atomic orbital, okay, whereas pi bond is formed by the sidewise overlapping of half filled p orbital only, okay. Now next, what we can say, the overlapping take place along the internuclear axis, as we have already told you. We go along the internuclear axis, right? The sigma bond is formed along the internuclear axis, but whereas the pi bond overlapping take place perpendicular to the internuclear axis, right? Like this, perpendicular to the internuclear axis, right? Now next is the extent of overlapping is large and the bond form is stronger, as we have already discussed. And whereas in case of pi bond, the extent of overlapping is small and bond form is weaker. Okay. Now next is if you're talking about the sigma bond, the molecular orbit formed as a result of the overlapping of symmetrical or as a result of overlapping is symmetrical about the internuclear axis. Whereas when we talk about the p orbital, the molecular orbital form as a result of overlapping consist of two lobes, okay, above and below the internuclear axis, as I have already shown you, right? Like this, there will be a two lobes like this, right? One is above and below like this, right? Two lobes. Now next is free rotation and no geometrical isomerism will form in pi bond and sigma bond, but whereas in pi bond no free rotation, geometrical isomerism is possible. Okay. Now again sigma bond, the bond can be present alone, whereas in pi bond the bond is always formed in addition to sigma bond. Okay. Now next is s and p orbital participate in the bond formation of sigma bond, but here only p orbital participate in the formation of pi bond. So I hope you have understood about the valence bond theory and the concept of sigma bond, pi bond and overlapping, right? So in the next class we will first discuss about the hybridization. After that only we will discuss this, okay, Vesper theory. Okay. In the next class we will discuss first hybridization. After that we will discuss about this valential electron pair repulsion theory. Okay. Till that, I hope today's class you have understood, right? So till that, thank you.